get going. So, welcome back to the second part of the morning session. I'm delighted to introduce one of the people who've been with us kind of for the whole time for these 2 months. Theodor Misiakiewicz will be talking about MeanField Theory of two-layer neural networks, dimension-free bounds, and examples.
Thank you, Dejan, for the introduction. Is it not too loud? Okay. It's kind of echoing. Okay, great. Thank you, Katie and Simone, for inviting me and for organizing this workshop. So I'll talk about MeanField theory of two layers neural networks, so dimension-free bounds and examples. So this is a work we did some time ago with Song Mei and Andrea Montanari. And also in this talk, I'll present some results from an earlier work by Song, Andrea, and Fan Min Nguyen. Okay, let's start. So for this talk, I decided to spend more time than usual on motivating and illustrating the MeanField framework. So I tried to design this talk keeping the audience of this workshop in mind. So I expect most of you to be very familiar with PDEs, but a little bit less with the theory of neural networks. So I start by reviewing some results on approximation theory for two layers neural networks. I then describe the MeanField description of SGD on two layers neural nets. I then illustrate this framework by working out one specific example, which is classifying centered anisotropic Gaussians. I then give some dimension-free bounds between the SGD dynamics and the MeanField PDE. And if I have time, I'll outline the proof of this dimension-free bounds. Let me start with the setting for this talk, which is just simply the classical supervised learning problem. We are given IID samples X, Y, Yi. So where the Xi's are vector of covariance of D dimension, Yi is a scalar response variable. And so we assume that this Yi, Xi are IID from like this common probability distribution that I denoted P. So the goal is to learn a model, F hat, so that given a new data point X new predicts the response Y new via F hat applied to X new. And we measure the quality of this prediction via the tensor with square loss. So I'll also call it the population risk throughout the talk. Usually we take F hat belonging to a parametric function class, meaning that F hat is parameterized by a vector of parameters theta. And so the goal is to find theta hat so that the population risk is small. And this is done, for example, by minimizing the empirical risk. So in this talk, I will forget about the empirical risk and only talk about the population risk. Okay. So as I said, we need, first to choose a family of functions. So this family needs to be rich enough to be able to feed complex data. And so in this talk, we consider the two layers neural networks, which is just this function. So 1 over n sum of sigma star x theta I. So n, so we have a big N, the number of hidden units on neurons. Sigma star is the nonlinear activation function. And it's parameterized by a parameter theta I that will denote collectively theta, like equal theta 1 to theta n. And so each theta I is of dimension big D. And so we have in total n times D parameters. So I'll just comment about the jargon. So two layers neural networks. So here we have one hidden layer composed of n neurons, followed by one output layer, which is just this averaging of the hidden layer. And so one standard choice is to take theta I equal to AI, BI, WI, where AI, BI are scalars. WI is a vector of dimension, same dimension as a covariate. And so sigma star x theta I is just AI times sigma inner product WIX plus the offset BI. And so we take sigma to be, for example, ReLU or sigmoid. So is this function class rich enough? The response is yes. So this is like, for example, a result by Sibenko in 1989 that proved the following universal approximation theorem. So given a sigmoid function sigma, meaning that sigma tends to like goes to 1 at plus infinity and to 0 at minus infinity, then what he proved, or like this is a slightly stronger modified version. So if f is squared integrable, then for any epsilon, you can find a neural network that is large enough and that has test error or like population risk smaller than epsilon. So there exists a sequence of neural networks that approximate the function arbitrarily well. Okay, so obviously this result is not enough to say that the 2 layers neural network function class is interesting. So the most important question is how big should n be for reasonable functions? And here is the celebrated Baron's theorem, so proved by Baron in 1993. So it's famous because it gives a separation between neural network and fixed basis methods. So in separation in terms of approximation power. So basically you take X, the distributed with a probability that is supported on a ball of radius small r. So you assume that the function f has Fourier transform big F, and then there is like approximation error. So the population risk is bounded by delta F squared over big N. So delta F is equal to 2 times R integral of this weighted Fourier transform. And so we see in this case that the number of neurons required to fit your function f, to approximate your function f, is bounded by this delta f squared over epsilon. So for fixed basis methods, you would need an exponential in the dimension number of neurons. So here, the point is that delta f can depend on the dimension. It can be exponential in the dimension, but for vast, interesting function classes, like rich function, this delta f will be independent of the dimension. And so you'll need only a constant number of neurons to approximate them. Okay, so from this approximation theory, we get some insights on the properties of neural networks. So first, the proof of the result from the last slides suggests that it's more insightful to think about neural networks in terms of a distribution over the parameters theta. So we write f at x rho, the expectation over theta of sigma star x theta with distribution rho. In the case of finite width neural network, we just take a sum of Diracs on the thetas. Okay, so one consequence of this representation is that small population risk is achieved by many neural networks. So what matters is rho, not theta 1 to theta n. And in particular, the behavior is insensitive to the number of neurons n, as long as it's large enough for rho hat n to approximate rho. Another thing is that because of Baron theorem, we see that the minimum number of neurons to achieve certain accuracy depends on the intrinsic regularity of F and not on the dimension D. So of course, all these insights concern ideal representations. And so that doesn't mean that we can reach them in practice. We can't construct them in practice. So in practice, what we do is that we train the parameters of the neural networks using stochastic gradient descent or its variants. So in this talk, I'll talk about SGD. So we initialize the weights theta I, IID from a same distribution rho 0. And at each step, we sample a new xk, yk from the training data. And we update the weights theta I as theta I k plus 1 equal to theta I k plus epsilon, the step size times the gradient of the square loss evaluated at xk, yk. So the question is similarly to the approximation theory. So what are the properties of neural networks reached by SGD? So for example, do they have small test error? Is SGD finding a near global minimizer? Or is it getting stuck to a local bad minimizer? Other question is, are these neural networks reached by SGD insensitive to the number of neurons, as long as it's large enough, and the dimension D, so similarly to the approximation theory. So these questions are fairly difficult, but there is a recent analysis that naturally connected SGD dynamics and approximation theory. So it was proposed in parallel by 4 different groups in 2018. And so this is MeanField theory. And so what they proved is that SGD dynamics admits an asymptotic description as the number of neurons goes to infinity and the step size epsilon goes to 0. And so in this limit, the SGD dynamics is described by a nonlinear PDE in the space of probability distribution on the space of parameters. Let me describe this MeanField limit. So first of all, we assume the following. We assume that we do a one-pass SGD. So the training examples are never revisited. So we denote the empirical measure over the theta ik, so the weights obtained after k steps SGD, one-pass SGD. So with step size epsilon. And so this initialization ID with rho 0. And so what they showed is that rho hat and t over epsilon, so the t over epsilon steps converges in probably weakly to in distribution to rho t. Okay, and this rho t evolve according to a PDE, which is of Makin-Vlasov type. So the partial derivative of rho t is equal to the divergence of rho t times the gradient of this potential psi theta rho t. So psi theta rho t is a sum of external potential v theta plus a pairwise potential, so u theta theta prime. And this is referred to as a MeanField description or distributional dynamics. And it has a nice mathematical structure. So this is a gradient flow on the risk R rho in the space of probability distribution endowed with a Wasserstein metric. So to make it more concrete, I wanted to give an illustration of this framework. So here I chose the following simple example. So we take a data distribution at yx, and we have with probability 1/2 y equal to +1. X is distributed according to normal distribution with covariance sigma plus, with probability 1/2 we have y equal -1, and x is a Gaussian vector with covariance sigma minus. And so we take this sigma plus minus to be equal to this U diagonal matrix 1 plus minus delta squared. So on the first S0 coordinates and 1 on the D minus S0 last coordinates U transpose. So U is an orthogonal matrix. So basically, we assume that the difference between y equal +1 and y equal -1 is the variance of x on this subspace spanned by the first S0 columns of U. So, and we call this subspace V, and we'll call PV the projection on this subspace. And so on the right, there is my artistic take on this classification problem. And so we consider furthermore this activation function, so just a ridge function. So sigma is just a function of the inner product of x and w. And so the goal will be to study SGD on this population risk. So let me just comment a bit this setting. So it's rather simple, and it will allow us to write quite explicitly the distributional dynamics. But it's not that trivial in the sense that so a good classifier would need to be able to find the subspace V. So meaning that SGD would need to be able to find feature, nonlinear feature sigma xw aligned with V among like many that are a priori equivalent.
2 points at the red points are the axis, right?
Yes, that's the dx.
And
So here it's a kind of high dimensional. So like projected from a high dimensional space.
Okay, so they are not.
So they're like on the. So that's why, for example, you can classify up to 0 risk, is because you have concentration on the shell. Yes.
Just to make sure, is it a typo that you don't have an AI outside, or is this just
No, there is no AI. So it's just much easier for the analysis. Yeah. But it's still like very difficult. I mean, yeah. That's straightforward how to analyze this SGD a priori. Okay, let me describe a bit more this distributional dynamics in this case. So in this problem, we have xy that is invariant under rotation on the subspace of V and the subspace orthogonal to V. So this observation allows us to simplify a lot the dynamic. So if we denote R1 the norm of W projected on V and R2 the norm of W projected orthogonal to V, then if the initial distribution rho 0 is uniform condition on R1, R2, then rho t, the solution of the distributional dynamic, will also be uniform conditional on R1, R2. So like rho t will have this form. And so, for example, this is the case if we take rho 0 spherical symmetric, which is usually the case. And plus, because of Jensen's inequality, global optimum will be of this type. So we don't need to look at other initialization. Okay, so the PDE of rho t now simplified to a PDE on rho bar t, which is 2-dimensional. And you can also write explicitly the PDE. And so we have a PDE in 2 dimensions instead of d dimensions. So we can efficiently solve it numerically, but we can also write it and classify the stationary points. And so Song, Andrea, and Fan proved the following, is that if we have some good initialization rho 0 bar and activation sigma, and they take the setting where S0, so the dimension of the subspace where you have a difference between +1 and -1, so S0 scale as gamma d, then so the PDE converges to a global optimal in a time t that doesn't depend on the dimension. It will only depend on delta, gamma, and the initial distribution rho 0 bar. Okay, so here I put some simulations from Song, Andrea, and Fan papers. So on top, so here we took like they take ReLU activation. So they add this AI and offset BI. And so now the distribution, instead of being 2-dimensional, it's 4-dimensional. So here the plot is the risk, the population risk against the number of iteration of SGD. And so you compare SGD, so the cross, and the PDE, so the continuous line. And for example, you see that, okay, like for delta, the 3 delta chosen here, you reach near 0 minimizer, so near global minimizer. And the structure of this, of the evolution of SGD is kind of complicated. So there is this flat region here, and this behavior is well captured by the distributional dynamics. So on the bottom, I instead of plotting some statistics, I just put like the distribution projected on R1. So blue is just the histogram, empirical histogram of SGD, and the red line is the solution of the PD. And this is for 3 different times. Okay, so one other thing is that SGD does not always converge to the global optimum. And thanks to writing explicitly this PD, we can find examples where SGD fails. So this is one. So here we take the activation function to be non-monotonic. So you have like this, first it drop and then go back up. And in this case, so we plot the risk against the number of iterations again. And so we start with 2 different initialization. So normal with 2 different variants. So kappa squared over d with kappa equals 0.1 and kappa equals 0.4. And what happens is that if kappa equals 0.4, you converge to global optima. If kappa equals 0.1, so you start very close to 0. And so the network with just a Dirac on 0 is a stationary point in that case. And so you see that you converge to this stationary point. So this is just all weights of equal to 0, basically. Okay, so after this example, so is MeanField a good theory for SGD? So first of all, one good thing is that MeanField is independent of n, which is an empirical observation, that SGD, as long as n is large enough, is fairly insensitive to the number of neurons. A second good thing about SGD is that in some cases, so for example, the example like this anisotropic Gaussian, it simplifies a lot the analysis. So for example, it factors out some landscape complexities of neural networks. So the permutation invariance of the neurons. It allows to exploit symmetries in the data distribution, which is not the case if you have only a finite number of neurons. And you can focus on studying a PDE, and so global convergence, stationary points, etc. And of course, for this approach to be meaningful, we need to answer the following question. So in what regime is the distributional dynamics a good approximation to SGD? And so, for example, if if in order for SGD to be well approximated by the distributional dynamics, you need the number of neurons to scale exponentially in the dimension, then it's a bad theory, because like as soon as D is a few dozen, the distributional dynamics will only model like very unrealistic large networks. Another thing is that in some examples, you can actually see that SGD is fairly insensitive to the dimension D, and that would not be captured by the distributional dynamics if it depends on D. Okay. So more concretely, so more precisely, so what we want to show is that we take theta k, so the weights after k steps of one pass SGD. So again, with step size epsilon and initial weights theta I0, ID with rho 0. And we denote rho t the solution of the distributional dynamics with same initialization. And so the goal is, so in this work, to compare the population risks. And so we want to be able to show the following is that for a given time horizon, big T, with probability at least 1 minus delta, we have the risk up to time T, the difference between the two dynamics, bounded by an error that is explicit in time, epsilon, big N, and delta, and other quantities. So here will be the assumptions for such a bound. So we'll consider the following type of activation function. So we'll take the parameters theta to be composed of a scalar A and a vector W of dimension big D minus 1. And so the activation function will be A times sigma X W. So here it's not necessarily an inner product between X and W. So we'll denote the potential V theta with factoring out the A. So it is V, W, and U, W1, W2 will be like this potential with this sigma activation function. And so we'll make the following assumptions. So those are fairly standard for people that know about like results in propagation of chaos. So we assume that sigma and Y are bounded. So with a little bit of work, you can show that sigma, you can take sigma unbounded. But okay. So basically here, if sigma is bounded, you can't take a ReLU, for example. Okay, so here, what we want then is for any W, the gradient of sigma with W is sub-Gaussian. So with respect to X. Then we, so in the second time, we assume that the potentials, there are differentiable with bounded and Lipschitz gradients. And the third assumption is that the initialization rho 0 is supported on, so for the parameter A, bounded. So we have like this constants K1, K2, K3. And so we'll consider two cases. So one is with general coefficients. So we initialize the parameters with this distribution rho 0. And we update both AIs and WIs during the dynamics. And the second case will be fixed coefficients. So we do the same initialization, but we only update WI and we fix the AI at their initial value. And so, for example, in the second case, the distributional dynamics will be D minus 1 dimensional instead of D. Okay, so the bound that we get is the following. So sigma star verifies the assumptions from the previous slide. So we take the time horizon T, okay, bigger than 1. And in the case of the fixed coefficients, we prove that there exists a constant K that depends only on the assumptions A1 to A3, so that with probability at least 1 minus exponential of minus Z squared, we get this bound. So K exponential of KT times square root log N plus Z over square root of N, plus this, which now has square root of D plus log N times square root of epsilon. In the case of general coefficients, we'll get exactly the same bound, but with exponential of KT replaced by exponential of KT cubed. So here I just rewrote the bound. So the first part is the error that is incurred by taking a finite number of neurons. The second is the error due to the discretization of the dynamic in time. So provided that T and K are constants, like of order 1, so the mean field approximation is accurate as soon as the number of neurons is large enough, independent of D, and large enough, like which only depend on intrinsic properties of the activation and data distribution. So only depend on this K. So this is kind of reminiscent to the Baron theorem. So in the Baron theorem, so the question is, how many neurons do you need to approximate the global minima? And here the question is, how many neurons do you need to approximate the like SGD dynamics? And so for the step size, we need epsilon smaller than 1/d. And so again, like a bit more explanation. So why did we call it dimension-free bound? So n does not depend directly on big D. So only on this KIs and okay, T. So the KIs, so this constants in the assumption can potentially depend on D. However, like in Baron, there is a number of settings that are interesting where these constants don't depend on D. And this is, for example, the case for this classifying centered anisotropic Gaussian setting. So I recall this covariance matrices, sigma plus minus. And so we have the subspace with the difference between the two distribution of dimension. So S0 equal gamma D. So I increase with linearly with D. We take sigma, the activation function, to be a truncated value. So I mean, you can take it a bit more generally, but basically this is an interesting example. And so we take the initial distribution rho bar 0 to have some good properties. So meaning that it has bounded density with respect to Lebesgue measure, and it has like somehow a good start. So the risk at with rho bar 0 is slightly less than 1. In that case, so Song, Andrea, and Fan showed that you converge in a time that is independent in the dimensions, and we can use our bound to get the following theorem. So for any eta, delta, big delta, and small delta, so there exists constant D0, C0, and T, so that for any D, so the dimension of the input bigger than D0, so which is a constant, the number of neurons bigger than this constant C0, and epsilon less than 1/d C0. Then if you take the number of gradient step to be T over epsilon, or stochastic gradient step T over epsilon, then with probability at least 1 minus delta, the risk at theta k is within epsilon from the global minima. And so here in this setting, we show that for a number of neurons of order 1, number of samples of order D, so one pass SGD finds a near global minimizer of the population risk. And so here I insist on population risk. So it's different than several other approaches that show that you converge to 0 training risk. So here in this framework, you directly show that the solution found by SGD generalizes well. And okay, so in this case, we were able to elucidate the dependency of the number of neurons and number of samples in terms of the dimension D. So unfortunately, these bounds are not quantitative in terms of the other parameters. So for example, eta, but it's already interesting. And so this is the global strategy. So to show quantitative global convergence for with SGD within like this framework is that you first show global convergence of the distributional dynamic. So there are some results that showed like some sufficient condition for it to happen. For example, Schuster and Bach. So the second step will be to bound the time to convergence, so TC. So here there is almost no results except like one with Javan Mad, Marco, Andrea from 2019, where they take a setting where the PDE is almost like near a PDE that is displacement convex. And so the third part of this recipe is the bound between SGD and the PDE. So right now, the bound that we have is exponential in T. So like this bound will only work if the time to convergence is much smaller than log n. So if it doesn't depend on D, basically. But okay, so this strategy already applies to some non-trivial examples. And so this anisotropic Gaussians was one of them. Okay, so like sometimes, so here I just briefly mentioned that so if you're interested in working on this MeanField description, you might want to choose a noisy SGD, which has like some interesting properties. So noisy SGD is basically SGD where you add Gaussian isotropic noise at each step. So they're independent and isotropic and have like this variance epsilon over beta. In that case, so the distributional dynamics now is simply the same with this extra diffusion term. So 1 over beta, so beta inverse temperature, and delta the Laplacian. And this again has a nice mathematical structure. So this is a gradient flow in the Wasserstein space of distribution for the free energy. So R rho, the population risk, minus 1 over beta, the entropy of rho. In that case, okay, so for this, when you add this diffusion term, then you can prove global convergence of the dynamic towards the global minimizer of the free energy. And under some regularity conditions, you can show that this global minimizer is also a near global minimizer for the risk function, R rho star beta. So if you take beta large enough, you'll also reach a near global optimizer of the populations. Okay, so in this for this noisy dynamic, we get similarly bound, like bounds between the SGD dynamics and the PDE. So for fixed coefficients, we get exactly the same bound. For general coefficients, so it's harder to control. So we get like, okay, it's a bit messy, but basically it's not dimension free anymore, meaning that you have like this D here, so you need N to scale bigger than D. And the second thing is that this band is now double exponential in T, in the time. So this band will allow to control this approximation up to a time T that is log N instead of log N for the other bounds.
Question.
Yes.
One more time, the difference, what you mean by the fixed
Oh,
coefficients?
so fixed coefficients, you fix the A, so you have activation function that is A sigma. And so you fix the A, so the sigma are just bounded now. So it's much easier to do the propagation of chaos argument. And for general coefficients, so what happens is that you have this coefficient in front of sigma. And so you need to bound how big they're becoming, basically. So here I have, I guess, some more time. So I just like briefly mentioned, like outline the proof for this dimension-free bound. So they're fairly like, not very complicated, it's just a bit tedious. So the ingredients is for this proof is so carefully isolating the different error terms. doing a coupling at initialization for different dynamics and doing like carefully concentration of measure arguments. And so basically the idea is we'll consider 4 different coupled dynamics and we'll bound the distance between each of them. And so the first dynamic is just you take n particles, theta I bar, which are initialized ID with rho 0, and you make them evolve with this velocity field from the distributional dynamic. The second dynamic, so you take n particles, so same initialization, so you couple them to theta I0, and now you make them so particle dynamics just gradient descent on the population risk with n particles. Then the third dynamic is just discrete gradient descent on the population loss, and the fourth dynamic is just stochastic gradient descent on the population loss. So one pass stochastic gradient descent on the population loss. And again, like all these 4 dynamics are coupled through the initialization. In that case, okay, so you bound the difference between the risks by using this dynamics as interpolation. And now it's fairly straightforward. So each time is some concentration like Asimov-Ding or McDermott's inequality followed by Grunwald's inequality. And so you can find the details of this proof in MeanField Theory of 2-layer neural networks, so from Colt 2019. Okay, final remarks. So MeanField Theory, so it's a theory that describes SGD for number of neurons going to infinity and like step size going to 0. So in terms of PDE in the space of probability distributions. So it allows to focus on key elements of the dynamics. So global convergence, stationary points, and in some cases it's very tractable. So here I presented some dimension-free bounds. So to approximate the SGD dynamics with the distributional dynamics, we only need the number of neurons to be bigger than a constant that depends on intrinsic properties of the activation and data distribution. I also emphasize that capturing this dimension dependence of SGD on neural networks is crucial in order to compare neural networks to other learning methods. So for example, kernel methods lately. And so there is a lot of open problems. So global convergence guarantees, bounding the convergence time. So improving this exponential dependency in T, going to multi-layer, et cetera, et cetera. Thank you. That's all I've prepared.
Questions? Good. Yeah.
I wonder about batch size. So I think what you're doing is batch size of 1, right, for SG.
Yes.
Yeah.
And this is not often used in practice because the noise is too large.
So
can you use larger batch sizes in the framework, and how do you?
If it's still one pass, there is no difference.
Sorry?
If it's a one pass, if you don't reuse samples, like all this analysis will go through. Yeah.
Yeah, I have a question regarding the global convergence guarantee. So other than the Langevin, other noise, is there any other like a normal result that can guarantee the convergence of the mean field dynamics?
So you mean other than Shiza and Bach, or
other than the Langevin algorithm?
Other than the
If you
so there are arguments from optimal transport. So by Shiza and Bach, and basically what they do is that they assume so first of all, they take okay, I guess 1 or 2 homogeneous activation functions, and they take an initialization that is isotropic, more or less, spread out, and they assume that that rho t converges to a row infinity. And so if you assume all of that, then they show that row infinity is actually a global minimizer.
Yeah, but that's is not equivalent of saying the convergence to, I mean, global convergence.
Oh.
You assume it's convergent.
Yeah, you assume that it's converging to a solution. But
I think that's very common.
Yeah.
Perhaps a comment on the Langevin result is that it's not just vanilla Langevin because the vanilla Langevin would give you convergence in time that depends on the number of neurons. Right? While here you get convergence in a time that doesn't depend on the number.
Yeah.
So that is
So this result on if you have a symmetry in your data set, and then in that case, like the PDE gets better, I suppose that this is more general, not just like the data set that you considered here. But maybe I'm asking, and then a kind of a follow-up is, so still the SGD is agnostic to this structure. Is that correct? Or does it, does the algorithm exploit this structure? And if suppose that's the case, what would be maybe a strategy to, if you don't know what the symmetries are, but maybe you believe are there somehow, how could this be perhaps exploited?
so I mean about this symmetry. So like here we took an example that is highly symmetric, just to simplify the like analysis, like analytical analysis of the distribution dynamics. But you might have like problems that are not symmetric and still have like this constant in the assumptions that don't depend on the dimension. So it's and you can have these symmetries and have constants that depend on the dimension. So this is kind of different, but just in this case, it was you can directly study the PDE instead of like using abstract arguments.
Yeah.
This is perhaps more of a comment, but I wanted to say you can weaken the design buffer assumption a little bit in the sense that you only need convergence of the function that is represented, and then you can show that the risk goes to 0, but obviously that doesn't tell you that you converge to a minimizer or in fact that you converge to anything. So you need a much weaker convergence only, and the
Without the noise.
without noise. So in retrospect, if I had known this talk before, I would have given a talk about that. But the other comment is that there are some newer results from, I think, 2020 from John Brunner, Zhengdao Chen, Eric van den Einde, and Brad Rotzkopf that say that if your risk decays quickly enough, you do not get this exponential blow up in time. So then you actually do get convergence for all time at or closeness for all time. But obviously, you make a strong assumption that the risk decays quickly.
what does it mean? The risk converges fast, then it converges.
If the risk decays, I think a little bit faster than 1 over t squared, and that's hard to prove. But then you don't have the separation from the discrete to the continuum.
You like in the bound, you don't have the exponential in t. Yeah. There's all like different ways of doing it.
But I think in this business, the really,
Yeah.
the really, challenging question is for which high-dimensional PDE. I mean, this whole business can work only if you have convergence in time independent of the dimension.
Yeah.
Right. So the really difficult mathematical question for PDE people here is, for which PDE I can prove convergence guarantees to global optimum, for which master sign flows in time independent of the dimension. So if anybody has ideas how to do these proofs, please give me a call.
Right, there we could continue, but I think we should move on. So let's thank